Welcome all of you again for the second lectures on viscous flow through pipes, which is quite interesting for you if you are preparing for GATE or engineering service. So, this part of the lectures, if you see, that's quite interesting in the sense that it has the applications of Bernoulli equations, it has the applications of momentum equations, also it has that how to approximate a complex flow through the pipe systems. So, that way I designed this course for you, so that you can have the feeling of application studies, how we can do it with knowledge of the fluid mechanics. So, I can say that these are the books what I am following more details in for these chapters, but you certainly you can have these two books which FM White and Sindel Simbala, they are the books at the higher levels, as you know we discussed earlier. So, today what I am talking about, that we are going for a demonstrations of the pipe fitting experimental setups which is there in IIT Guwahati. Again I will revisit the virtual fluid balls. Then we will talk about the minor losses in the pipe systems, and again I have to revisit it what is called energy gradient lines or the hydraulic gradient line, which is more important when you are solving this pipe network problems. Then followed by I will solve the few problems on pipe networks using Bernoulli equations, linear momentum equations and the pipe loss equations. That is the example problems what we will solve solving the losses in the pipe fittings and all. Let us go for the next level slide. Again I am repeating these slides to just to energize to you that when you have the pipe flow, most of the times we have the turbulent flow. Okay. So, whatever the pipe flow you consider it, always we have the turbulent flow, as you can visualize the turbulent flow of high turbulence, low turbulence zones, high turbulence and the low turbulence zones. When you talk about the turbulence, do not look at the figures like this type of vortex phenomena and all. Always we quantify the turbulence with respect to Reynolds numbers. The Reynolds numbers, if it is greater than some threshold values, then we call the turbulent flow. That means the Reynolds numbers, when you talk about that, it is a ratio between inertia forces and the viscous forces. For pipe flow, what we have the Reynolds numbers, which is rho v d by mu, the inertia force by viscous force. These values, if less than 2300, the flow is laminar. If Reynolds numbers greater than 4000, the flow is turbulent. Okay. So, please remember this threshold for the pipe flows, but for other flows you can have the higher studies to look at that. So, if it is a Reynolds number less than 2300 and Reynolds number greater than 4000, we have a laminar and the turbulent flow. In between you have a transition flow systems, and you can see here the photograph of showing how turbulence vortexes are there or eddies formations are there. So, we can visualize that, and today many of the best fluid mechanics labs, they have the facilities to measure this type of turbulent structures, the quantified, that how much of energy dissipated because these turbulence structures. So, looking this is as just a introductory to start our things. Just I am taking one of the example of water supply schemes from L&T Construction's web page. You can see this, the planning of water supply systems. You just look it. So, there is a source, there is the supply systems, there is a source points and there is a supply at the individuals, the house level. But for that, if you look at that, it will be a series of the tanks. What is it dedicate? The series of locations where you will have a augmenting the additional energy in terms of pumping the waters. The additional energy you want to give to the flow systems and store these waters. Then you have a second line of, again you have the tank systems. So if you look at these systems, which is look at the water supply system, is like a power grids. So when you plan this type of water supply systems, we need to know how much of loss is happening it, how much of pumping is requirement is there, how many overhead tanks are we should design it, what should be the network of these pipes, what could be the diameter of this pipe, and what type of pipe should be there. All these things, these complex systems, what we design it to make it so that this totally should have the least energy driven system. Okay, that means it is a combination of pumping and the gravity flow system. So you will have a certain systems, you will have a pumping systems, then you have also the gravity flow from that. So all these component of these water supply systems, we need to find out how much of energy loss is happening it, and what will be the available discharge at the different points, like considering this point, what will be available discharge at this point. So these analysis, if you look at that, what we are discussing it, those are very preliminary levels. But when you design this type of water supply systems, there are commercial softwares or the free softwares are available, so that you can design these systems to know it at each point, what will be the available energy, what is the amount of discharge will be available. All these things you can quantify under different scenarios, like you have a summer water supply system, winter water supply systems, where you need different amount of the waters. So all the things we consider it, considering this basic, the pipe flow what we are discussing, it's that. So with this note, let's go for the next slides. On the next slides, what I am showing it that how we conduct the experiments to quantify the how much of losses are happening, energy losses is happening it. So if you look it, we call major losses. Major losses, that is the losses due to the frictions. So that way, if you look it, there are the two pipes are there, and in these two different pipes, there are the manometers are attached to determine what is the pressure difference at the 2 points. You just closely look it. So as we will measure the pressure difference, and as you know the how much of discharge is going through these pipe systems for a steady flow conditions, we can compute the velocity, we can know the pressure difference, then we can quantify the energy losses just following Bernoulli's equation with some modifications. That's what we will discuss. So basically these type of systems we have to quantify what is the amount of major losses. But there are minor losses, like this is the band is there, a loss will be there. The band is here, there will be loss. Here also we have the band, and there are the valves are there. So all these are called minor losses, as well as there will be the exit lost or contractions lost. All these loss components which are called the minor losses, that what in terms of energy, how much of energy losses when flows going through that. So those things also today we will discuss it. So these are the experiment setups. The students conduct the experiment with a different discharge and find out, measure the pressure difference, and with a simple calculations they quantify it, how much of energy losses or the head losses happens for minor component as well as the major components, like the 5 due to the frictions and the fitting, the elbow, the bends, the exit, the valves, all we consider it to find out how much of energy losses are happening it. Now let us go for the next slides, which is again I will talk about virtual fluid balls. Here again I have to repeat it to tell you the virtual fluid balls to understand how the vortex formations happens within a pipe flow systems. Okay. Like the last class I discussed about the pipe flow systems when I am considering it, a pipe, a horizontal pipes, and because of the turbulence how the eddies formations happen. These are eddies. These are eddies formations happening, and those what we try to understand, because if there is a horizontal flow, it's going out, and we quantify it in terms of the balls moving with disintegrated integrated concept. But for to define the streamlines for a complex fluid flow problems, today we'll use to same virtual fluid ball concept to define the flow streamlines, because as you know it, when you try to apply the Bernoulli equations, the first assumption is that you should apply along a streamline, or if you consider the flow is irrotational. So, it is very difficult to quantify the flow is irrotational, but always we can draw a streamline like these cases, and I can apply the Bernoulli equations. That is what today we will discuss more when I will give you the applications and also some few example problems. Now, let us go back to the Louis Moody, 1944 in Princeton University, USA. What he has developed is from the experimental data. If you try to look it, he has not pulled out only his experimental data, but long back the data from others researchers, all the data he combined it for the developing these Moody's charts to compute friction factors, compute the friction factor of the flow through the pipes, mostly these commercial pipes what is used it. So, now if you try to interestingly look at these things, which is I can say that is a knowledge of the fluid mechanics. If you try to understand these curves, it's representing the knowledge of the fluid mechanics in a just to compute the friction factors. If you look at the friction factors, here we have a Reynolds numbers. The x-axis is Reynolds numbers in a logarithmic scales, and the y-axis we have the friction factors, which is a normal scale. If you look at this part, what it is indicating for us, the first condition is laminar flow. This is the laminar zones, as I repeatedly showed that this is up to 2300s. So, the relationship between the friction factors and the Reynolds numbers, you have F equal to 64 by Reynolds T. So, it is a linear functions, you can see it that. But when you have a transition zone which is 2300 to 400, 4000s, in those regions we cannot compute these friction factors, because so fluctuation behaviors are there. We cannot compute it. If you compute it, there will be a lot of erroneous which will be there, as the experimental data is showing it. So, most often when you design the pipe systems, we avoid to have laminar flow and the transition zones, because in the transition zones the frequency factors can fluctuate very wide range from this to this, and most of the times we design the flow which is the turbulent flow. Okay. Then it can start from smooth pipe to rough pipe. That means it can start with a relative roughness which is E by D, that means roughness by the D values can have very, very small to 0.05. Each lines are representing for you the 0.05, 0.4. So, this is the turbulence zones part. Now, if you look it, try to understand it, as you know it, the friction factors for the turbulent flow is a functions of Reynolds numbers and relative roughness value. What it is there? If you look at that function dependency is there still at this point after the pipe we call rough pipe zone. That means after that the friction factors as a single functions of only the relative roughness, not it does not depend upon the Reynolds numbers. Now, if you try to understand the physics wise, what it happens is, as we increase the roughness, then the Reynolds numbers which represent you the V d rho by the mu, this part does not have a much significant, the viscous effects are not significant, more the effect of the roughness is comes it. The mu components not much significance, as you are going more the roughness, it becomes independent to the Reynolds numbers. That is the reason it is a constant, independent to the Reynolds numbers, it is just depend upon the roughness values. So, we divide into two zones. One is a transition zone where the friction factors is depends upon the Reynolds numbers and the relative roughness. Now, you try to understand it, that if you have increase the relative roughness of and the higher Reynolds numbers, it depends upon the friction factors only these relative roughness, not the Reynolds numbers. These things you can conceptually just think it, that how the process happens it. I am just leaving to you. So, these diagrams what is prepared from the experimental data, not from only from his data set, also the data set what was prepared from the artificially glued the roughness pipes in Germany. They combining all the data, Europe data and the USA data. He prepared this map which still date mostly used, we have been using the charts to determine the friction factors, because once you know the friction factors, it is easy to compute energy losses. So, once you know the energy losses, then you can quantify it, that what type of pipes we need it, what type of diameter pipe you need it, all we can link with the energy losses. Now, if you look at, if you do not have this chart, okay, then there is two parts. As I say that for the transition zone, there is a developed equations like this. Okay, you can see that it is called implicit equations, because the friction factors also here, okay. So, we cannot directly compute the friction factor, because it is a implicit equations which is there in both the sides, and it is also non-linear and implicit equations. Okay. Because of that, nowadays we can estimate these ones, because there are a lot of mathematical tools are available, like the Microsoft Excels and all. We can iterate it and compute it, what will be the F value if I know the E, you know the D, and if I know the Reynolds numbers. So, we can compute it. It is not that difficult today's when you have a good computational facility with us. But when you go for the rough zones, which is, as I already said, that it has a functions of only the relative roughness factors. That is what is defined it here. So, you can use for this part for the transition zones, this is the part you can use for the roughness zones. But earlier for the smooth zones also we can approximate like this, which is explicit equations. That means you just substitute the Reynolds numbers, you can get the F value. Okay, you can always debate it, what is the difference between these two. This is the approximations of this part. It is valid for certain reasons, but the exact equation is that this is the one. Okay, so that's what is the Paul Blasius 1915 from Germany. That's what he's developed it. We can explicit equations, you can develop it, which is just substitute the Reynolds numbers, you will get the F factors. But for getting the accurate F vectors for the transition zones, we can use these equations, which is nothing else, the fitting of the Moody's charts, and similar way you can get it for the rough regions, the equations. This is also is derived from the Moody's charts. So, if you do not have the chart, you use these equations. If you have a chart, you do not need to compute these equations. Directly you can get it the values from the chart itself. Now let us go to the minor losses in the pipe systems. As I told it, when you have the pipes, it can have a regions, you have a smaller pipe to bigger pipe or bigger pipe to the smaller pipe. When you have these conditions, that means the flow is coming it here and going out, the smaller diameters and the larger diameter. If you have these conditions, what we do it that when you compute the energy losses for these total regions, we compute the energy losses these terms here. You can understand each energy losses will have a functions of p square by 2, which is kinetic energy per unit mass into a factors which will be responsible for how the flow patterns, how the streamline patterns, how the vortex patterns are changing it. If you know that, you can quantify it or you conduct the experiments. It's very easy to conduct the experiment of different pipe diameters, different configurations. You can compute it. You just measure the pressure at these 2 points and you know the velocities, like the manometers you can put it, then you can measure the pressure difference and you can easily quantify it, that how much of K value from experimentally. That's what it was done so far to compute this K value from experimentally. But for your point of view, I am just explaining it how the flow process happens within the pipes. Now let us look at how it happens. That again I am considering virtual fluid balls. Okay, if I consider the virtual fluid balls, the balls which is going very close to the wall, which will go straight and inject here as a tangential and go like this. Okay, what will happen to this? Here also you have the particular liquid, but that liquid will have a vortex formation. They will start rotating it. So majorly your flow will pass these regions will have a vortex formations. Because of these vortex formations, you will have energy losses. You will have the energy loss, the additional energy loss you will have because of this vortex formations are there. And the quantity of the vortex formations, the quantity of the energy losses happens, it depends upon the D1, D2, V1, V2, what type of flow is happening. Because your streamline patterns will change depending upon the V1, V2, the flow Reynolds number, energy, what is the energy is coming this. So from the experimentally for different D1, D2, we can compute it how these things are changing it. From experimental data, we can get it the energy losses in terms of V square by 2 into the K part. So basically, we are compute or experimentally we are getting the K value. Now we go to the next ones. It's quite interesting. If you have a bend, most of the times we avoid the bend, but it's okay. Looking the topographies and all, we need to have a bend the pipes. So when you have the bend the pipes, okay, the flow is coming like this and it's going like this. You can easily draw the streamlines, okay, considering this the balls, virtual ball. Similar way, this is like this. If this in these regions, the vortex will be there. This is for energy losses. This is because of these vortex processes are there, that's what is additional energy losses will be there. Those energy losses is depend upon what is the angle of these ones. This is case is 90 degree. So if you have a different angles, the zone where the vortex is happening, that's what will be the different. So the angle of this part also depends upon what is the flow is coming, that also depends upon. But on average we consider it even if you have this case. But if you looking these figures, what it's saying, how to avoid this vortex? It's easy. You make instead of straight 90-degree elbow, you give a curvature here, which will fit it exactly this part. If you do that, the pipe systems with a, then there will be less energy losses. So instead of having just 90-degree bend of the elbow, we can have a curve at this point. You can give a bend 5. So that what will be the lesser energy loss as compared to these ones. That's what most often in industries use it. But if you look at that, we have the T joint. That means I have the discharge is coming Q1 here and the Q2 is here, okay, and this is the Q3 which is going out, okay. Looking these figures, you can say that Q3 is equal to Q1 plus Q2. That's not a big issue for steady flow, okay. But let us look at that inside what it happens. It depending upon, if this you look at, if flow is coming like this, the flow will follow this and go like this. This flow will come like it's good, and here this vortex zones will be there. And this flow what is coming it, they will come like this. And this is what? The mixing zones. This is a very interesting phenomenon if you can look at that. Many of the times if you look at that, if there is a two fluids are there, if you just put a two fluids, okay, fluid is like maybe this is waters, this may be the oil or something, you can see how the mixing zones is happening, how the vortex zones is happening. It can easily quantify it. So now if you visualize that, so now if you look at that, because of these mixing layers, because of the vortex formations and the presence of the vortex formations, you can feel it if you are engineers, just touch these pipes, you can see this heat is generating it. You can see the temperature difference. So that means indirectly it indicates for us there is a vortex formations are happening it. The energy dissipations are happening it. So we can identify which are the regions are the heat generating it, or it's so those regions you can identify, and also we can measure this vortex phenomena. And but more of the times we just try to look at that how much of energy losses is happening to this case, HL part. Okay. So we can define in terms HL is equal to K times of V square by T. This K we can put it with the different configurations. That's already experimentally done it. So there are the table, we just follow it. But interestingly, let's go for these two systems, okay, which I intentionally putting to you that just look at these figures. One is expansions, another is contractions. The flow comes from this side and goes like this side. In this case also flow goes like this. Now if you look at the streamlines, which is just closer to the wall, in this case it happens like this, we already discussed it. But if you have a contractions, then what it happens it? There will be vortex zones here, there will be vortex zones here. So you can understand it that more energy losses will happen when you will have a contractions, okay, when you will have the contractions. But in case of expansions, the vortex zones are the less. So energy losses in this case which will be much higher as compared to the expansion zones because of the vortex formations. But if you can make it the shape of like this, okay, a gradually variations or gradually expanding it, then you can avoid the energy losses what is going to happen because of this vortex phenomena, similar way like this. But exactly to have these shapes is very difficult, okay. And as this in a pipe flow, we don't get a constant velocity, there is a fluctuating velocity. There is like the flow varies it, because water demand varies from the winter to monsoon to the summer seasons. So we vary the waters to design exactly the face of what will be the shape of the outer streamlines are very difficult. So mostly we take a trade-off between that, and you try to make it as closer as possible to have a less energy losses because of this part. I just highlighting here to show you streamlines, okay, to tell it. Now if you look it, I am just talking about how to use linear momentum and Bernoulli's equations, which is energy equations. So, to apply these energy equations, what I should do it? I take a streamline. Along the streamline, I should apply the Bernoulli's. So, most appropriate streamline is these ones. You take it this, because these are horizontal streamlines. So, we can just know the pressure and the velocity, and modify the Bernoulli's equations, apply over these ones, not here or there. Okay. Similar way, if I want to apply the linear momentum equations or the mass of conservations, I should consider the control volume is much bigger than affected area, so that I can get it, this effect should not be there. So, I can use this control volume to apply the mass conservation equations or linear momentum. Exactly same way I can use this control volume still up to this point, apply it. Please do not take the control volume like this, which is totally wrong, because you do not know it, these zones, what is happening. So, when you take the appropriate control volume, you should look it. That means you should look at the control volume where the streamlines are the parallels. Streamlines are parallel. In this region, the streamlines are not the parallels. So, you try to avoid to draw these outer streamlines, find out the regions where they are not supposed to have the streamlines having any curvatures, the more or less the parallels. Like this case, if I draw the streamlines, all will be the parallel by the time we reach it here. These regions I can consider, this part, and this part anyway, it is not difficult for us because there is no flow boundary conditions. So, to take a appropriate the control volumes, we should have a knowledge of how the flow happens it, how the flow behaviors are happens it, where the vortex is happening, where the flow lines, the streamlines are parallel. You consider that by visualizing this flow like this or this, then you try to look it. So, what I do encourage you to that, whenever you get a problems, you try to draw the streamlines and find out where is the locations we can have a vortex formations. If you try to understand that or try to draw that sketch, you solve the 20% of the problems. Another 20, I can say the another 20%, maybe 50% of problems. Another 50% is that how to apply mass conservation equations, linear momentum equations, and the Bernoulli's equations, which it's not that difficult to apply it. So, basically the strategy is that you should try to understand these ones. If you look at that, most of the times also we have a valve to control the flow, okay, which is a gate valve, okay, it is a gate type of systems. If you rotate it, this valve closes the waters, okay, and it can have a total open or half close and all these conditions to regulate the flow. To regulate the flow, we have these systems. Now, if you look at, if I want to draw the streamlines, how it happens it? So, streamlines will come like this. Okay, there could be the vortex formations here. And if you try to understand it, that I have not this open or the totally closed, if the half open, your flow distributions, you can understand it, how the streamlines patterns will come, how the vortex formations will have. Either you open it or close it, but half close, half open will make it as the flow process at this process is difficult, or the more energy will dissipate as compared to other conditions. Now, if you look at similar way, we have the globe valve, which is more control valve systems. The flow comes here, then rotate it, and this valve it goes off and flow goes like this. So we can look it now in terms of vortex formations here, the vortex formations here, and once flow goes it also could have the vortex formations also here. If you look it that way and just compare two valves, one is globe valve and the gate valve, this required for different type of discharge conditions. So if you look at these conditions, you can easily interpret it will have a more energy losses for this case as compared to these ones. But we need sometimes this type of valve to control the flow systems. Let us come for derivations of energy losses and the pressure and velocity distributions of having a systems where two pipes are we are enlarging it from the smaller diameter to bigger diameters. If you have that conditions and you can draw the velocity distributions. The velocity distribution it depends upon the type of the flow. If you have a laminar flow, the velocity distribution is different. If you have a turbulent flow, velocity distributions will be different. That's what we will discuss in the next class. So we will have a velocity distributions here depending upon the type of the flow. And then I try to understand it to draw the streamlines, the flow separations point and the vortex formations. So I will consider the control volume as I said it earlier, where I have a streamlines are this part, or I can consider the outer this one is my control volume part. I can consider it that, or I can consider this is my control volume. The most of that will use the linear momentum approx. That way we will apply it to compute it. So the basically what I am talking about here, this is what is our control volume, and we will apply mass conservation equations where since this is incompressible flow, density is a constant. So mass conservations will be the A1 V1 and Q2 will be A2 V2 and Q1 will be the Q2. The two locations will have the discharge is the same because of mass is conserved. Now come it to this, I am just applying the linear momentum equations for these control volumes. Okay. So if you have this is my control volumes, so you may have the shear stress is acting on this. Okay, this the shear stress part. Okay, but we are neglecting this part. We are neglecting the shear stress part. Just we are assuming the pressure difference between these is equate with a momentum flux. This is what we have derived lot. So this is a rate of change of the momentum flux is equal to the pressure difference between the pressure force difference between this P1 and P2, and that what if you rearrange it you will get it this part. Okay. So it's very simple equations that we are using this the linear momentum equations applying over these control volumes along this line and neglecting these shear stress components. Okay, because this is a very short reach. Okay, that's because of shear stress whatever the force component will come it much smaller as compared to the pressure force and the momentum flux components. This is the momentum flux component what we are equating it V2 and V1 directions. If you use that you get it this part. Okay, which is very simple, just to rearrange the part and you will get it that. Now I will applying Bernoulli's equations along the straight line. Okay, I am just applying the Bernoulli's equation along the straight line. When you apply the Bernoulli's equations, means this line is horizontal, the streamline is horizontal, so you don't have a jet components. You have pressure head component and the velocity head component. That's what you equate it at the P1 P2, B1 B2 plus energy loss components, the head loss component. So the flow is come from the one section to sections 2, where through the flow there is energy losses. That's what we quantify with HL. So because of that we call it's a modified Bernoulli's equations. It's nothing else. you are equating the energy, you know that how much of energy losses is happening, so you are just incorporating the energy losses at the sections 2, that should be equal to the energy at the section 1. So that is very basic equations, but we are incorporating directly this energy losses, what we compute from major loss or the minor loss. If we substitute that, finally you get energy losses, so or the head losses in terms of the velocity and the d2 by d1, if you can look at the dimensions, okay, and the theta angles, okay. So the k varies with these parameters, which is very easy to quantify it, which is a functions of d2 and the d1. The same way, if you have a gradually contractions happening it or gradually analyze that, you can compute these values, okay, and sudden contractions happening it, you can have this type of calculations, you can get it with a simple applying these momentum equations. Now if you look at the tabular values what we have, and here I am talking about the head loss is equal to the k b square by 2. So this k value, how does they value it? First is gate conditions, which is 0.18 can vary up to 0.10 as the diameters increases. Same way, if you look at that gate valve, which is 0.18, 7.80. So we can understand it how much the globe valve and the gate valve, the energy losses will be there. It's much larger, but as you increase the diameters, it can reduce it. Similar way, you can have 90 degree, 45 degree, the elbow, you will have different quantity of energy losses. The 45 degree, we can understand it, it should have a less energy losses as compared to the, this is 90 degree. So if you have a 45 degree, you can draw the flow, the streamlines, vortex zones, you can understand it, the vortex zones will be the lesser as compared to the 90 degrees. So this is less as compared to this ones, this is less to this one. So what I am highlighting it, these are things you should understand from the tables. Don't look at the table, it's just data, we should use it to further things. But these tables give a knowledge to us how the flow patterns are happening. Similar way, if you have a T joint, you will have a different type of the energy losses is happening. So these are the experimental data to get it this energy losses coefficient of k, and if you know the v velocities, you can compute it. What is the minor loss or minus energy losses? Again, I am repeating it, this energy gradient line and the hydraulic gradient line, what we discussed just after the Bernoulli equations. Now let us, I have the reservoir, okay, this is the datums. From the reservoirs, I have the pipe systems, okay, and there is a pumping system. So you can draw hydraulic gradient line, also we can draw the energy gradient line. The hydraulic gradient lines will have the jet plus the pressure head, okay, plus if you look at the velocity head, we will get it the energy gradient lines. So now if you look at that, as the pipe fluids goes down, you will have this drop of the potential head, that's what will be drop is there. Similar way, if you look at that, there is a pump systems which is increasing the energy. This is the increase of energy because of the pumping systems and increase of the velocity. That's what will be making this energy gradient line. And if you can see, there is a slope, that is the major losses. What is happens it? The frictional losses that will be represented to us the slope components. The major losses will be there. So any pipe flow systems, you can sketch it tentatively what is the energy gradient line, what is the hydraulic gradient line. These energy and hydraulic gradient line talk us that how the flow patterns are happening it, where is how much of velocity of the flow, and what is the amount of energy is available at different points. Okay. So we try to understand the sketching this energy gradient line and the hydraulic gradient lines. That's what is important. See, because as I said it earlier, today pipe designs and all the things are necessary, but there are a lot of softwares are there, mathematical models are there. You can compute this, the design a pipe networks. But as a engineers, always you should look at the hydraulic gradient line, energy gradient line. Then you try to interpret it. How much of velocity is there? How much of energy available for different conditions? So that interpretations we should do it, and we should always try to sketch this energy gradient line, the hydraulic gradient lines. And if you are good master in how to draw the energy gradient line and the hydraulic gradient lines, you could be a good designer, pipeline designers and all. So now let's come back to the questions. Okay, the examples what we have. Okay, so the first example is very simple. Is there is a pump, okay, and which moves this amount of the waters per second. That means discharge is given to us through a pipe diameter is given is the pump discharge pressure is this much, okay, kilopascals. What must be the pressure of the flow entering the device at the position P? Okay, that's need to be computed that, and there are pipe dimension of 800 meters, 322 meters, 800 meters is connected with a two junctions where you have energy losses. The K factor is given to us with a valve also. K factor is given to us. So we'll apply the basically we'll apply modified Bernoulli equations and the energy loss equations or using the Moody's charts. Based on these two, we can find out if you know this pressure at this point, you know this total energy available at this point. If you compute the energy losses is through this pipe because of frictions, also because of the junctions and because of the valve. If I know the total energy losses on this, I know energy at this point, then I can compute energy at this point. Once I know what is the available energy at this B point, then we can easily find out what could be the pressure. That's not a big difference. Okay. So let's come back to so first I say that we should have a modified Bernoulli equations with the head loss components. Okay. Modified Bernoulli equations with the head loss components. First what you do it, we should compute the flow Reynolds numbers. Okay. So here we are substituting within terms of diameters and we are computing the flow Reynolds numbers, which is coming out to be so large numbers. Okay. This Reynolds numbers is much larger than 4,000. So the flow is turbulent. Flow is turbulent. It's not a big. Okay. So you can quantify it. What is happening the flow at this series? This value is much larger. This flow is turbulent. So we can use Moody's diagram for solving the problems. Okay. So that's this is the Reynolds numbers, and we are confirming it that is a flow is turbulent. Also we are trying to we will use the Moody's diagrams to compute in that. So this is a commercial steel pipe. So roughness value is given to here. The relative roughness value is know it, and once you know the relative roughness value, we are getting it this value, and we are computing the relative roughness values. If I know Reynolds numbers and the relative roughness value, I can compute it what will be the friction factors from Moody's chart. It's very easy. Identify this approximately, which the curve will come there. You know this Reynolds number, computed that, draw the lines with matching that, then compute these friction factors. Okay? It's very easy. Using these Moody's diagrams, you can first identify with respect to the relative which curve we should follow it, but if curve is not there exactly, we can interpolate it that curve and know the Reynolds numbers, interpolate it this, then you get it the F factors, which is the friction factors we are getting it. So once you know the friction factor, then the problem solving is quite easy. Okay. So that means I know the head losses, That's what is computed here by substituting this value. There will be minor losses like bend losses, valve losses, the entry and exit losses, all the components. This entry and exit loss we don't consider here, only the bend loss and valve loss we compute it, which we have these values. If I are considering that, the loss components will get it, this much is the minor losses. Now we are substituting Bernoulli's equations, the modified Bernoulli's equations, to compute what could be the pressures. So I am not going more details, as you can read this PPT to get it details. So once you know it, then you can compute the pressure. Just substitute its value, then compute the pressures. So it's quite easy job now once you know that. Now you take it the second problems, which has the GATE 2015 problems, is that the pipe of 0.7 meter diameters has a length of 6 kilometer, connects to the two reservoirs, okay, and the water level in the reservoirs is 30 meter above the water level of reservoir B. Okay, halfway along this pipeline there is a branch, water is after the third reservoir C, then friction factors of the pipe is given, the quantity of the water discharge into reservoir C is given it. Considering these accelerations due to the gravity is this value, neglecting the minor loss, the discharge into reservoir is what? Okay, that's what is the questions. If you look at that, you draw the sketches, that is a 6 kilometers, happen this D is given, and you have a 0.15, this is the discharge what is coming. If this is a Q amount of discharge, this will be Q minus this part, okay. So you know this part. You also know these two reservoirs having the elevations difference of 30 meters. That means this much of energy loss has to be there, otherwise these two level cannot be maintained. So when flow comes from this 5 of a Q amount of the waters, which is passing through this 0.15 on this, but total head losses, total energy losses from through these pipes should be the 30 meters. Then they do have the 30 meters elevations difference will be there, because velocity at this point and this point will be the 0. So the total this value will be there, or I can say it will have some sort of the hydraulic gradient or energy gradient like this. So we need to try to know it, that what could be the Q value such way that we will have the energy losses of 30 meters when passing through this 6 kilometer long pipe. For that, F is given to us. Okay, we know this, the length, we know the F factors value is given. So we just substitutes to compute head loss, because this amount is a Q amount of waters and this pipe will be Q minus 0.15. Okay. So you will compute the head loss, that's what we have derived it, and you compute this head loss components. Sometimes we write in terms of Q, but or you can write in terms of V, that's not a big issue, and you can compute the energy losses in this should be equal to 30. That's what I was discussing. That is the key point of these problems. Okay, the energy losses of this sector and this part should have, this is Q amount of discharge is going, this is Q minus 0.15. So you get it this value. If you solve it, you will get the Q value, and if you know this Q value, you can compute the QP. It's not this. The tricky of these problems, the hints of the problems are only these ones, nothing else. Another, the third examples. Okay, two reservoirs are connected with a 930 meters. That is a gate. Again, this 2015 papers. The diameter 5, which has a gate valve. Okay, it's having the valve here. Okay, the pipe entrance is sharp. The loss coefficient is given it. The valve is half open. Loss coefficient is also given. The K is given here. Here also K is given. The head difference between two reservoirs is given it. Again, same problems. Okay, assuming the friction factor is given, acceleration duty has given, it's approximated here, and you have to find the discharge accounting all the major and minor losses. If you look at these problems, is exactly for the problems what we discuss it, nothing else. Okay. Here we have a major losses and minor losses. All these losses will equate it to compute, find a total energy losses, which will be the 20 meters. That's the problem. The F is given, the K values are the givens. So you will write in terms of discharge and compute it, what will be the, will use this energy losses, frictions losses, entry losses, exit losses, valve losses, all components are there, and if you substitute it, you will get the velocity and you will get the discharge. So the substituting value and all, you try to understand it. It's okay. It's not a very difficult task for you. And with this, let me finish these lectures with giving, acknowledging their contributions, having so beautiful PPT and illustrations for you, delivering these lectures of fluid mechanics. Really, I enjoyed lots delivering the lectures, because it has a lot of illustrations, lot of examples and all. And at the days, there are the summary, as you know it, we discuss about the minor losses of the pipe. We also show you the experimental setup. We also derive that minor losses, how to this. More important, you could energy in and hydraulic gradient lines which need to be drawn it, and also you can use the control volume concept and you try to understand the flow. It's not microscopically, also the gross characteristics ways. With this, let me thank all of you for this attention. Thank you.